So in this video, I'm going to be talking about something called power series, which is a special type of series. They're called power series because they involve a power function. So notice in this, here's an example of one. There's both an n and an x. So n is the variable that goes with the series, or the sigma notation. So n is the indice of the sigma notation. So n is going to automatically step up 1, 2, 3, 4, 5, 6, all the way to infinity. Whereas x is a different variable. It's actually the x variable, just like if you think of for graphing, the x-axis, it's associated with that. So it's some variable that I can replace numbers with. So you can see that this really represents like a family of series. That if I change, when I change x, it produces a different series. So for example, if x equals 1, then we have this series, n running from 1 to infinity of -1 to the n times n over 4 to the n times 4 to the n. And you can see the 4 to the n cancels out. So, however, if we had x equals 2, then we have n running from 1 to infinity of -1 to the n times n over 4 to the n. And this part here, the x plus 3 to the n, would be, if x equals 2, that would become 5 to the n. So you can see that x leaves us room to create different series. So this power series really represents kind of a family of series. And so our goal generally is to find either the radius of convergence or the interval of convergence. That's the two things we'll talk about. So radius of convergence or interval of convergence. So generally, we talk about radius convergence. Radius, you think of a circle, right? Convergence. If you think about a circle, the radius kind of represents how far from the center we can go. And the interval of convergence would be just the interval of x values that this series converges on. Okay. Now, back to the radius convergence, when you talk about the radius convergence, usually you need a center. So the way these power series works is they always have x minus the center somewhere in the expression. So in this case, the center would be -3. So that's the radius. The radius convergence is, so C is the center of this power series. So the radius convergence would be how far from C can I go and still have convergence. So the way we represent that is x minus C, absolute value, has to be less than some r. So the r would be the radius convergence. So we're looking for, again, we use absolute value when we want to talk about a distance or how far, right? Because this would be x minus c would be, whatever my x value is minus the center. And then that distance, if it's less than the radius convergence, then it converges. If x minus c is greater than the radius of convergence, then it diverges. So here it converges, here it diverges. Now, if x minus c is equal to r, well then we're not sure. We have to think, because sometimes the series converges on the edge of that r, and sometimes it doesn't. So but the basic understanding you have is that if it's less than r, as long as x is closer to c than the radius of convergence, it will converge. That's how the radius convergence is defined. Okay, so then the interval convergence would be just an interval of x values that fall within that range. So let's say, for example, that my radius convergence was 3. this is all generic now. We'll get to the problem in a minute. But so if we have x, and let's say the center was 2, so that means that as long as this thing is less than 3, we have convergence. So if you think about, since the center is at 2, I can go 3 to the right of it and 3 to the left of it. So that means the interval of convergence would run from, let's see, 2 minus 3 would be -1, and 2 plus 3 would be 5. So that would represent the interval of convergence. Now again, we don't know what happens when it's equal to r, so we'd have to figure out whether the edge points are included or not. But for now, we know that this would be the interval of convergence, because it's 3, because this is saying the radius is 3 and the center is 2. Okay, so that's a general idea. Now let's look at this specific one. So we can tell right away that the center is -3, right? Because of what we just talked about over here, right? And just, I want to make one other point. Notice that really what we have here is a polynomial. That's what they call these power series. Because notice that all of this stuff in here really is a bunch of numbers. Because we know that n, even though n looks like a variable, but we know that n is going to be 1, 2, 3, 4, all the way to infinity. So if we actually were to figure this out, this would be a big polynomial, right? Because I plug in 1 for n. If you plug in 1 for n, you get what? -1/4 times x plus 3 to the first, right? If you plug in 2 for n, you would get, 2 over 16, which would be 1/8 times x plus 3 squared. And you can see we could just keep doing that. You create a polynomial, a polynomial with an infinite number of terms. So if a polynomial with 3 terms is a trinomial, maybe this would be an infininomial or something like that. Infininomial? No, I'm just kidding. There's no real name for that. So actually, there might be. I just don't know. Okay, so let's get to the actual business at hand here. We need to come up with the radius convergence and then therefore the interval of convergence. So we're going to use, so since this is a series, we've been working with infinite series before, so we have methods for determining whether a series converges or not. And this, if you look at it for a bit, it involves power. It involves a polynomial and an exponential, which generally we use the ratio test for that. So we're going to go ahead and see if we can figure out where this thing converges. So notice, normally we're figuring out whether it converges or not, but because we have this x in here, now we're going to figure out where it converges. See the difference? If there's no x, we can say this either converges or diverges, but as we said, this is a family of series, so we're going to figure out which part of the family converges and which part of the family doesn't converge or diverges. Okay, so we're going to do the ratio test. And remember, we always say the name when we're doing it. Ratio test. So that means I have to take the limit as n approaches infinity of an absolute value of -1 to the n plus 1 times n plus 1 all over 4 to the n plus 1. And then we're going to divide by a sub n, which means I'm going to flip it over and multiply. So I'd have 4 to the n on top. Oh, oops, I forgot mine. That's embarrassing. Forgot my x plus 3 to the n here. So then we're going to multiply that by 4 to the n over -1 to the n times x plus 3 to the n. That's it, right? Okay, so let's simplify some things for a minute here. So the -1 to the n and -1 to the n plus 1 is going to give me just -1. And of course the n plus 1 doesn't cancel out. We'll leave an n on the bottom. The 4 to the n plus 1 and the 4 to the n, all the 4's will cancel out except for one of them, so that'd be a 4 down there. And what else we got? The x plus 3 to the n plus 1 and the x plus 3 to the n. That's just going to leave an x plus 3 on the top. And I think that's everything. Okay. The absolute value takes care of the negative 1. It's not going to have any effect because it's just being multiplied through, so that will have no effect whatsoever. So we really have the limit as n approaches infinity, absolute value of n plus 1 times x plus 3 all over 4 to the n. Now, here's the interesting part. So, when I'm taking a limit, remember if I have a limit of, say, 5 times f of x as x approaches infinity, that's the same thing as 5 times the limit of f of x as x approaches infinity. Remember that? If I have a scalar multiple, I can move that in or outside the limit. And so we're going to do the same thing here. Now, what's the scalar multiple? Well, of course 4 is, but that's not what I'm talking about. Actually, what I'm talking about is this part right here. I know it doesn't look like a scalar multiple, but remember, my limit is in terms of n. So I'm letting n approach infinity. That means that x plus 3 is stuck. It's not going to move. So, so that means I can move it in or outside of the limit. So I'm going to write this as, now of course it's still absolute value though. So I'm going to write this as absolute value of x plus 3 times the limit as n approaches infinity of absolute value of n plus 1 over 4n. Now I could have took the 4 out if I wanted to too, and you certainly could do that. I just wanted to get the x plus 3's out of there, just because that way I can evaluate this limit pretty easily. And notice this is the limit of n plus 1 over 4n. Since they're both the same degree on top and bottom, we just look at the ratio of leading coefficients. So we end up with 1/4 here. So this would be the absolute value of 1/4 times x plus 3. Whoops, I made that wrong. Okay, so that's the limit. Now remember in the ratio test, we are looking for this to be equal to 1, and it's not equal to 1 right now, but because there's an x in there, right? So what we really want is for this to be less than 1, because we're looking for convergence. So what we're going to say, we're going to figure out what x values make this less than 1. So again, usually when we do the ratio test, we just get an answer. This is a number, and we just say, is this less than 1 or bigger than 1? If it's less than 1, we get convergence. If it's greater than 1, we get divergence. If it's equal to 1, the test fails, right? So what we're going to do, since we're interested in convergence, we're looking for the radius of convergence or the interval of convergence. We're looking for convergence, so we want this expression to be less than 1, because that would cause this whole series to converge. So now we're going to use some algebra. So if I have an absolute value of 1/4 times x plus 3 less than 1, I can multiply both sides by 4. That's not a problem with absolute value. So then I'd be left with the absolute value of x plus 3 is less than 4. Now, this looks familiar to something we've seen before, isn't it? Notice when we're talking about radius convergence, this is how, when we're talking about radius convergence, it's x minus the center, absolute value less than, or r. So this expression here actually gives me the radius convergence. So we would say the radius of convergence is 4. Okay? And since the radius convergence is 4, we know the center is -3, right? Because remember, x minus c, that gives me that expression's always going to show up in the power series, where c is the radius convergence. So the radius convergence, is the center of the power series. So radius convergence is 4. And the center is at -3. So if you go 4 to the left of -3, you get -7. If you go 4 to the right of -3, you get 1. And so that gives us initially the interval of convergence. Okay? Now, notice if you solve this inequality expression, you'll get that same answer. Because remember, the way we solve absolute value inequalities is we say that x plus 3 must be less than 4, or x plus 3 must be greater than -4. Those two inequalities come from this one absolute value inequality. And notice if I subtract 3 from both sides, I get x is less than 1. And if I probably should be and actually, not or. And at the same time, if we subtract 3 from both sides, we get x is greater than -7. So the solution to this inequality would be x has to be less than 1 and at the same time greater than -7. And of course that gives you that same answer. But I think it's easier once you get to this spot to just recognize that 4 is the radius and -3 is the center, and so then you can come up with the interval of convergence. So this is the interval of convergence initially. Now we're not quite done yet. And this is power series is a little bit more involved because we end up doing 3 different tests. So see, the problem with the ratio test that we just used is if it's equal to 1, we don't know whether it converges or not. So there's still this question mark on these brackets. They might be square, they might be round, because we don't know. The ratio test doesn't tell us whether it converges when it's equal to 1 or not. So what we're going to have to do is we're going to test the endpoints now. So we're going to say, let's pretend that x is equal to -7 for a moment. Then we're going to rewrite our series. So we run n runs from 1 to infinity. I already forgot what the series was. -1 n times n. -1 to the n times n. Thank you, honey. Over 4 to the n. And notice we put -7 in for x, we get -4 to the n. Okay. So now we're going to say, okay, let's let x equal -7 for a moment. And we'll do this again with x equals 1 as the other endpoint, right? But we're going to just look at this. So now this is just another series. It's not a power series anymore. It's an actual just normal series with nothing but n's in it. So we're going to try to evaluate whether this thing converges or not, because this will determine whether it converges on the left endpoint or not. The power series converges on the left endpoint or not. And this will tell me whether the power series converges on the right endpoint or not. Okay? So here we go. Let's simplify it a little bit. So we're going to run n from 1 to infinity once again. And notice that if I pull a -1 out of here, right? So this would be -1 to the n times 4 to the n, right? Because if I take -1 to the n and 4 to the n and multiply them together, I'm going to get -4 to the n. And so notice I have -1 to the n here and -1 into there. So if I multiply -1 times itself n times, that's just going to be 1. So this turns into just n times 4 to the n over 4 to the n. Of course, 4 to the n over 4 to the n is just 1. So this really just becomes the n equal 1 to infinity of n. And you could think of that as a p series with p equal to -1. So this is a p series with p equal to -1, because we could rewrite this as 1 over n to the -1, which that's a funny way to write it, but in order for it to look like a p series, that's what we do. And since that is less than 1, this thing diverges. So that tells me I can go back up to my interval of convergence and I can erase that question mark. This is a soft bracket on -7. Okay, so now let's go back and do it with 1. So if x equals 1, then my series becomes this guy. 1 plus 3 is 4 to the n over 4 to the n. Now this time I don't have to take out any little special little -1 factor out. 4 to the n's just cancel out essentially, and I'm left with n running from 1 to infinity of -1 to the n times n. And this we can actually use the nth term test on, right? The limit as n approaches infinity of -1 to the n times n, and that does not equal 0. It just gets bigger and bigger, even though it's hopping. It's going, you know, it's hopping back and forth, positive, negative, but it's getting further and further away from 0 as it goes. So this definitely doesn't approach 0. So therefore, this series diverges. So we confirm the other question mark. So the answer to this question would be the radius convergence, if they ask for that, is 4, and the interval convergence would be just like that with soft brackets. So that's power series. I'm going to do another example here, but you can see these things are pretty involved. They take a lot of space. I'm going to do a different one, see if we can get a different result. N equals 1 to infinity of 2 to the n over n, and times x minus 2 to the n. So the first thing you want to do when you're doing power series is ask yourself, what's the center? And you can see here that the center is 2. So remember, we're looking for radius convergence or interval convergence. So we're looking for the x values where this converge, or we're looking, or the other way to think of it is how far from 2 will this converge. And again, these are x values, right? Okay, so once again, we're going to use the ratio test, which we will on, I think all the ones we'll do in this class will be ratio test. You can use other tests, of course, but we're going to use that. Keep things simple. Okay, so the ratio test, the limit as n approaches infinity, absolute value of 2 to the n plus 1 times x minus 2 to the n plus 1 all over n plus 1. Multiplying that by n on top, 2 to the n on the bottom, and x minus 2 to the n on the bottom. That's the value. Simplify like we usually do in the ratio test. We're going to go limit as n approaches infinity of, now the 2n and the 2 to the n plus 1 cancel, leaving just a 2. These guys cancel, leaving just an x minus 2. And the n and the n plus 1 do not cancel at all. And so we're going to pull out the stuff that we can. So let's say we got 2 times x minus 2. This time I took the 2 out. Again, it doesn't really matter because it'll show up as your answer to your limit, or it'll just be a part of the stuff you pulled out. So this is, of course, going to be the absolute value of 2 times x minus 2 times the limit of this as n approaches infinity is just 1. So that'd be times 1, so I'll just leave it. And so that's my limit of the ratio test. And remember, what I want from that is for it to be less than 1. So I'm going to put a little less than 1 right there. get that 2 out of there, so I divide everything by 2, and I get the absolute value of x minus 2 is less than 1/2. And there's my radius convergence. We can recognize that scene, x minus c times less than r, right? That's what we're looking for, to recognize the radius convergence. So we'd stop here and say radius of convergence is 1/2. So then we also know that the interval of convergence is going to be a little bit before 2, 1/2 to the left of 2. So that would be 1.5, I guess. And a little bit to the right would be 2.5. And then the question is are these brackets soft or hard? So I'm just going to put soft in for now and see if we can put little question marks there so we don't know. So then we're going to go test the endpoints of our interval. So again, I'm going to say, okay, let's let x equal 1.5 for a moment. And so then I'm going to rewrite my series. So that's going to be n running from 1 to infinity of 2 to the n. What is it doing? 2 to the n over n, and then my x minus 2, if I put 1/2 in there, 1.5 minus 2 would be negative 1/2 to the n. Okay? So this is we have to evaluate whether this series converges or not. So this looks like maybe an alternating series test. Let's play around with it a little bit. N running from 1 to infinity. If we pull out a negative 1 from there, that'd be negative 1 to the n. We'd have to pull out n negative 1s from there. And that would leave me with 2 to the n times 1/2 to the n all over n. Now, 2 to the n times 1/2 to the n, that would be 2 times 1/2 n times. Well, 2 times 1/2 is just 1, right? So this would be 1 to the n. So we end up with the series n running from 1 to infinity of negative 1 to the n over n. And that's a pretty easy alternating series test. So we're going to go down here and say, okay, alternating series test. My a sub n is going to be equal to 1 over n. Because remember, the a sub n is what's left is the same as the sequence, except for not alternating. So then we need to show that thing is decreasing. A sub n is definitely decreasing because 1 over n plus 1 is definitely smaller than 1 over n. And the limit as 1 over n, as n approaches infinity, that's definitely 0. So we fit the two requirements of the alternating series test. Therefore, this series, n running from 1 to infinity of 2 to the n times negative 1/2 to the n all over n, converges. So then we go back up to our interval of convergence, and now we're going to erase that question mark and erase that soft bracket and put in a hard bracket, because it actually converges when x is equal to 1.5. And we still need to test the other endpoint. So we'll go down here and say, let's let x equal 2.5. And then my series is going to be n running from 1 to infinity of negative 1 to the n. No, what am I saying? I forgot what the series was. It's going to be 2 to the n over n. And the x part, if I plug in a 2.5 in there, 2.5 minus 2 is 1/2 again, but it's positive this time, right? So n equals 1 to infinity. Of course, 2 to the n times 1/2 to the n. That's just 2 times 1/2 n times, so that's 1 to the n. So that would just be 1 over n. And this is divergent. You could recognize this as a harmonic series. That would be enough, because that's a known series. We haven't talked about that much, but I think I said that at the very beginning. Or you could call it a p-series with p equal to 1, which is greater than or equal to 1, which that makes it divergent. So then we go back up here, erase this question mark, and my interval of convergence would be from 1.5 to 2.5, including 1.5, but not including 2.5. So again, what that means is that this power series, this original power series, as long as you're at 1.5 up to, but not including 2.5, those series will converge. Anything outside of that will diverge. So anything outside of this interval, if we plug those numbers in for x, the original series will diverge. Anything inside this interval, if we plug it in for x, the original series will converge. Okay, so that's the introduction to power series. You can go ahead and try your hand at it. There's a good video, or there's a good worksheet in the modules, and go ahead and have some fun.